Okay, let's continue with some storage-related stuff. I'm Johannes Thumshirn. I work for Damien in the system software group of Western Digital Research, and I mainly work on the BTRFS file system for several years now. And recently, BTRFS gained support for zoned block devices, and well, there's that ominous write hole we have in BTRFS, which is why BTRFS still has a bad reputation. So let's try to close the gap and close the RAID write hole and give BTRFS a chance to do rating on zone block devices. A bit of an outline of the talk. Some background on BTRFS, because I'm assuming not everyone is totally familiar with BTRFS. Same for zone devices. And then some background on the zone append operation, which recently got introduced with the CNS standard. And then how BTRFS on zone devices works. And then we go on to a problem statement with lessons learned from RAID in the last decades, and then what the proposed changes are, how we could make RAID better, and how the design, I think, should look like, and then some current status with some screenshots. Because I'm not doing a demo, I didn't sacrifice my children to the demo gods. So, small refresher on BTRFS. BTRFS is a copy and write file system. It's based on a B tree that is copy and write capable, which give us some neat properties like snapshots and subvolumes are dirt cheap. It's just a ref link. Additionally, we do have some advanced features like data compression with several different compression algorithms. We can do checksummings of metadata and data. I think data checksum, BTRFS is the only Linux file system that actually does data checksums these days. We do have built-in multi-device support, like a logical volume manager and a RAID layer, which does RAID 0, RAID 1, RAID 10, RAID 5, RAID 6. Although RAID 5 and RAID 6 MakeFS currently warrants you if you try it out. And we have a utility called BTRFS send receive, which just takes a snapshot of the tree and of the on-disk tree and dumps it to standard out, so you can pipe it to tar or via SSH to a different host and do your backups, or some hyperscalers use this to do updates of containers throughout their whole fleet. So what's zone block devices? Zone block devices are today most commonly found in form of shingled magnetic recording HDDs, and just recently CNS SSDs. They're defined in SCSI with a CBC, and ATA CAC, and NVMe CNS command sets. And a zone block device works by dividing its LBA space into zones. For hard disks, we have conventional zones, which act basically like you'd expect a hard disk to work. And there's then the sequential write required zones, where you can only sequentially write a line to a write pointer, kind of like how a tape works. And to rewrite old data, you have to reset the whole zone and restart writing. So you have to be aware of this rule in order to write to zone block devices, because you can't just do random I/O inside a zone. Random writes. Random reads still work. As this is a bit cumbersome, especially you can't really go high queue depth, the zone append write operation was defined, and which it is a kind of a nameless write. So you tell the command, just place the data in this zone, and on completion, tell me where you wrote it. which for us as file system people, it's awesome because it's our extent allocator in the drive, not in the file system. Awesome. So you can go really high QDEP, say, in this example, QDEP 3, well, it's not really high, but just dispatch several commands to a zone. The drive tells you where it wrote the data, and then afterwards we can build our metadata and write the metadata. In kernel 5.11, we've landed the first support for zoned devices on BTRFS, which mainly assembled around the superblock. So the superblocks are the only on this data structure in BTRFS that is on a fixed location, which didn't work. So we had to reserve 2 zones per superblock and make a ring buffer. So you can always look at the right pointer and see where your latest superblock is, kind of like a log-structured file system. Then we just aligned the block groups to the zone sizes and wrote a small extent allocator, which just looks if there's enough data in a particular block group and gives the block group. Then with kernel 5.12, it's fully functional for HDDs, meaning we do zone append for all data writes. For metadata, we unfortunately can't because BTRFS uses hard-coded offsets in its B-tree structure, so we need to have at least per block group log and do normal write commands. But unfortunately, we can't do all features regular BTRFS has yet, meaning we can't do no-cow, which we will never be able to do because due to the nature of zone devices. Currently, no fallocate because we don't have in-memory pre-allocation of extents, so it's always on-disk pre-allocation, but that can be fixed. And up until now, no RAID support, which is what I'm talking about today. With kernel 5.16, we gained support for the CNS standard, which basically was just 2 things, but zone capacity being smaller than the actual zone size. And then we are respecting the max active zones limit the drive gives us, so we are not trying not to overcommit too many zones. I'm giving the drive a hard time. Then currently we're more or less in a stabilization phase. We made some automatic reclaim to get garbage collection ongoing, and which will be available soon in regular BTRFS as well, because companies like Facebook found it relatively good for regular BTRFS in some situations, so they activated it. And then there's lots of corner cases. We're still hitting bugs, but well, it's software. We'll never be completely bug-free. On to the RAID problems. So one of the biggest problems for BTRFS RAID was the disconnection between the file extent layer and the RAID layer. So especially for RAID 5 and 6, every substripe write did a read modify write and not a copy on write to save some calculation time for the checksum for the RAID syndrome. So this created a RAID write hole if there was an unexpected power loss between the stripe writes. So we need to always do copy and write, and the copy and write needs to know about the RAID situation and vice versa. And ideally, this should work for no-cow files and no-cow file systems as well, for the regular BTRFS case, for the non-zoned. Another problem that we in for zoned rate found is that BTRFS expects a deterministic data placement for rate. So the offsets from the block group starts have to be the same on each block group, which with a zone append operation we simply cannot guarantee because the drive decides. So multiple writes will just race, and we're getting problems there. Another problem common to all RAID implementations these days is the rebuild stress. So if one drive is failing and you just rip it out the system, place the next drive in the system, you have to rebuild the RAID. So all drives in the array will get reads to it to rewrite the new drive. This stress makes it likely to happen that one of the good drives starts failing as well. With today's drives being 12, 15 terabyte, it takes some time to rebuild the RAIDs. And then there's pretty inflexible encoding schemes like RAID 5 doing only an XOR operation. And RAID 6 is basically just an XOR and a shift for the second parity, for the Q stripe. So I did have some proposals how to address all of these problems. These were just for the rebuild problem, we could just distribute the data placement and just add more disks. Well, working at a drive vendor, that's probably the solution my employers like most. Add more disks and try to distribute the data. So if you have like a RAID 1 with 4 disks, if one disk fails, we can still evenly spread out the load to the other disks, making it less pressure, less likely for one of the other disks to die. Then just always copy and write to get rid of the write hole. So no more substripe writes, etc. And for this to work, I have to introduce yet another tree. Well, we already have 13 trees in BTRFS, so a 14th tree. Well, go on, it's just a little bit of metadata. And this allows us to use zone append for data writes on RAID as well, because we can record the location of the data and then just have like a plugin framework for parity algorithms to be able to do no parities for the RAID 0, 1, 10 case, the classical XOR and PQ stripe parities everyone knows from RAID 5 and 6, and then some new fancy stuff like erasure codes or MDS codes, butterfly codes, whatever people like these days. So you have more than 2 blocks of parity information and can build fancy 5 data, 16 parity, or whatever. Whatever you like. So let's get a bit into detail about each of these changes. So for here would be the distribution of the data placement. Well, that's a traditional RAID 6 with 2D, 2P, 2 data to parity. And if we are just declustering it, we are spreading it, try to evenly spread it out over the disks. So if, say, this disk is failing, you only need to get this parity, which can be calculated from these 2 disks. So it's 2 reads to calculate the parity for the new drive. No stress for the other drives. Less likely to have drive failures in these. Another thing, this is to get rid of the write hole, which is the biggest pain point we have in BTRFS RAID 5 and 6. So just add a stripe tree describing every on-disk stripe with some additional metadata. It will be written after the data has reached the disk. so in BTRFS, we are writing all metadata after the data, similar like, I think it's ext4 in the data equals ordered mode. So this can be seen as a journal layer, but not a write-ahead journal, just a post-prior journal. And this tree basically just does some logical to physical translation with a start length tuple mapped to a disk start. And then we can do the rest of the translation later. Here's some. As this part of the tree is like the biggest change, I'm dedicating the most slides to it. So when we have a file with several extents, and one extent is the first 3 megabyte, we are writing disk 0 gets the first megabyte, disk 4 second megabyte, third megabyte is at disk 3. Disk 6 and 7 get the parities. And that's like the physical representation. And that's the on-disk metadata representation. So we are keying the B tree entries by the logical length tuple of the file extent, which means we have a extra metadata consumption of 16 bytes per disk in the RAID set. So for an example RAID with 3 data blocks and 2 parity blocks, it's 80 bytes per extent. So 80 bytes additional for stripe tree nodes, which we can still fit 51 of these tree nodes into one disk sector, or one 4K disk sector. This design might not yet be the final version. I have RAID 1 implemented. It works for RAID 1. I'll send an RFC to the Linux BTRFS list soon, so we can discuss it, if this is a feasible final version. Here's some more mapping details. So firstly, on this side we have the BTRFS file extent item, and the disk byte number and disk num bytes will map to the key for the B tree, being the object type, object ID, being the disk byte number, and the offset in the key, the size of the extent. This then gets us a DP stripe, or a distributed parity, BTRFS distributed parity stripe, which has several extents in it, and maps back to that dying PowerPoint. Come on. Seriously? Oh, wow, where's my mouse pointer? So. Okay. Nope. That's so. Okay, apparently Microsoft doesn't like BTRFS being an awesome file system. Yep. Yep. So this is basically your, like in an SSD, you have these logical to physical translation layers in a classical SSD, but it's just lifted into the OS, into the file system of the OS, basically. Nothing too fancy, but nothing we currently have yet. This has some advantages, some disadvantages, of course. It's a very scrub-friendly address translation, so we could just run scrub. It's still going all through the page cache. You can check all our on-disk checksums. We have a journal, a ordered update journal. It's very similar to how we already handle checksums in BTRFS, where we are calculating the checksums of all written extents prior to submitting it, submit the checksums, then record it in an extra checksum tree. And on read, you recalculate the checksum, check against the checksum tree to see if the disk actually broke your data or the HBA. There's actually quite a lot of HBA firmware that was discovered to be broken thanks to BTRFS. There is no implicit connection needed anymore between the substripes in a RAID set, so we can do zone append on drives that on zone drives, and we can easily do higher reliability with M+K failure codes by just having special erasure codings. Of course, downside is we do have additional metadata, but 16 bytes per disk is not too bad, I think. And we could still merge consecutive sequential on-disk stripe extents, but that will give us different problems for ref links. So I'm not sure if we want to go that route. Then for the configurable parity algorithms, I don't have too much yet because I haven't started with that one, but that will just be like a plugin framework where you just register your parity algorithms inside the file system and have do the math on every read and write, like we currently do with the checksummings, plugins or checksum framework and the compression in the file system. And so it's very similar to how we handle compression, but kind of unlike compression because we are not shrinking the data, we are adding data. So it's anti-compression. The very current status, already said, RAID 1's implemented. Still have some rough edges, but yeah, doing DD or XFS IO works, doing FIO doesn't work yet. Or FS stress survives like a minute, which is not too bad for the early stage. For metadata on RAID 1, we don't need to do zone append, so we don't need stripe entries for metadata, only for the data block groups. So I don't need to do metadata for metadata. That's why I started with RAID 1, because I'm still not sure how I do metadata for metadata. Read ahead still gives me some troubles because read ahead is trying to batch consecutive on disk extents, but the translation might not be always correct, so it gives me checksum errors. I think that should be solvable within the next week. Then RAID 0 will be next. And once RAID 0 and RAID 1 work, I hope RAID 10 just falls into place. So fingers crossed. And some screenshots. I hope that's kind of readable. So we can actually try to make it a bit bigger. Currently, you still have to set the runtime feature to on MakeFS time to have a RAID stripe tree, which will stay there for regular BTRFS, and some BTRFS will have to automatically just pick that runtime feature, otherwise RAID won't work. Then mounting. Here I did some a small 1 megabyte write to a non-existing file. Here you see the stripe entries. Here's the logical address and the logical size, which maps to 2 different devices with their respective physical addresses. Here's like the next then. It's a very trivial tree. And fscheck also works. So you can create the file system and it's actually working. And it also can check some scrub works too, but I think I don't have a screenshot for scrub. No. Any questions?
Algorithms interchangeable, so I can actually switch them out because the hashing is not possible.
You can already do that.
You can switch out the hashing for. So the hashing, these checksums you can't switch out, but you can do the RAID. Yeah, I know, but you can for the read Solomon and so on if it's more storage use basically.
Well, you can still just convert the file system to different RAIDs that BTRFS balance, and then.
Yeah, okay. Because you can't switch the checksum from CRC32 to something else. It has to be done on creation time.
Yeah.
That's why
not yet. Which I forgot back in the day when I made the additional checksums. I totally forgot about that one. But I think someone inside SUSE is working on it.
Good.
It's either BTRFS tune or BTRFS balance. So I think Drew from SUSE or Gabriel, they are working on it. Yeah, apologize, I forgot that back then. So this time for RAID, I won't forget it. Just I'm even planning for the RAID 5.6 cases that you can, just like the free space tree used to be in BTRFS, that you say like a mount option or a BTRFS tune flag to say, yeah, just give me a RAID stripe tree, convert your on this file system to get rid of that write hole, which hopefully makes people happy again with BTRFS and RAID. Anything else?
You also had encryption on the slide, which hasn't been a feature as of yet.
Oh. Did I have encryption on the slide?
It was a U8 encryption.
Okay. Well, the U8 encryption, it's in the extend item since the beginning.
Okay.
I don't want to spoil too much, but there's people working on encryption.
No, I was talking to him about that. I was also talking to him about hot zones where you could offload to SSDs, so you can have spinners and SSDs. But I think he said they had something running on Facebook, but they haven't released anything.
I'm not sure about Facebook. I know Facebook has something running about encryption, but there is patches for that from some Italian guy on the list.
Yeah, but this was also the hot zones, as in just having a cache. Yeah.
So yeah, it will be coming.
Good.
Once
everything else.
What's everything else? Well, I'm concentrating on the RAID stuff. I know the Facebook people concentrate a lot on the encryption stuff. Performance.
How about jumping between different RAID levels? Start with RAID 1 and then add cases?
Well, that's already possible. So with regular BTRFS, you just plug in a disk and say, okay, now when I have RAID 1, add a third disk, just give me a RAID 5, and it will rewrite your data. So that, of course, should still be possible because I don't want to lose features.
So the parity algorithms you're thinking of reach almost on, I don't really know how well behaved those are. I mean, how well would that work? How many devices would it cover and so on? It would cover more than RAID 6 anyway.
Yeah, so for it to really make sense, it should be more than RAID 6, but we have a team doing a lot of algorithms research and erasure code research inside WD, and I already got them hooked to the project. They're very keen to help.
It's good. It's really good.
Having your on-staff mathematicians is sometimes kind of helpful. They've also promised to provide like assembly accelerated code for the kernel. So let's test them.
Yeah.
Okay.
Okay.
Thanks.
Thanks.